Hello again, welcome to the Academy. This is part of a video series on Calculus 3 topics, and this time we'll be talking about cylindrical and spherical coordinates. So last time I talked about triple integrals, and in fact, let's just start with an example right away. Consider we wanted to find the volume of a region. And this region is bounded from below by the function x squared plus y squared, which, as we know, looks something like this. This is the bottom, and bounded from the top by 4 minus x squared plus y squared. This is going to be sort of an upside down version, starting at 4. And so, there we go. So this is our region, and to find the volume, all we have to do is take the integral of dv, and we should have, so our region is, this region we call it v, where the volume is, so volume v region. And it's pretty easy, you may think, to set up the bounds. We can easily start with, well, on the inside we know we're going to go from this bottom function to the top function. They already gave it to us. It's already given our two functions. dz. And then we're going to have to integrate the shadow of this region to find the rest of the stuff. But we know that the shadow of this region is really a circle, as you can sort of visualize, but to verify that, let's actually find this curve of intersection. So when do these two intersect? Well, when they equal each other. So 4 minus x squared plus y squared. When does it equal x squared plus y squared? Well, we can just add it to both sides to get 2x squared plus y squared equals 4. X squared plus y squared equals 2. Next, we all know a circle with a radius square root of 2. So integrating over a circle is not that bad. But as we know, we would prefer not to use dy dx for this, because we would have to do something like, well, y goes from negative to positive 2 minus x squared. And we can put it right here. And that would be negative square root of 2 to square root of 2. But clearly this is not the best way to do it. As we've seen before, when we're dealing with circles and stuff like that, it would probably be preferable to use some form of polar coordinates. We would actually integrate this region dA using polar coordinates, which would be much easier. As we know, the polar dA is r dr d theta. And we integrate that, which gives us what the angle goes from 0 to pi, r goes from 0 to square root of 2. And that, of course, is much simpler than this. Is the same thing. And this, in fact, what we're doing right here is really using cylindrical coordinates. Cylindrical coordinates is a coordinate system. I'm using a different color for this just to show cylindrical coordinates. As the name suggests, is based on a cylinder interpretation of a three-dimensional space. So you have z, but it's a polar form of 3 dimensions. So basically at every point Z you have a circular slice. So at every point Z you also have R, and of course the angle they come out, theta. So every point in space can be described by coordinates of r, theta, and z. And of course, we have some pretty easy ways to get back to our usual x, y, z coordinates, because each slice here, each circular slice, will follow the same rules as in polar. This is just going to be x is going to be r cosine theta, y is r sine theta, and z is itself z. So this coordinate system is pretty basic, and as we know, when we want to integrate in cylindrical, we often have dv equal to r dr d theta dz, or any other combination of these instead of the usual dx or dz dy dx, or any other combination of those, permutation. I mean, you can imagine pretty easily how functions would look in this one. Cylinders would be easy to describe. For example, the function r equals 1, that's just a cylinder with radius 1. As z changes and theta changes, r just gets fixed at 1. Again, all the other polar functions will look similar, except they'll be cylindricized, you could say. So every polar graph, you can imagine it being stretched in the z direction. That's cylindrical. But there's another way to generalize polar coordinates into 3 dimensions, and that is called spherical coordinates. And use another color for this. This one is useful, as the name might suggest, describing spheres. So in spherical coordinates, you have the distance from the origin. So any point is the distance from the origin, and that's called rho. The Greek letter rho is used. We also use the zenith angle and the azimuth angle. So one of the angles is the same angle as in polar. It's from the x-axis so imagine this little triangle here. It's this angle theta again. That's the one angle. Then we have the zenith angle, zenith being from the top straight up. The angle down from the vertical is phi. So we have 2 angles and a length here. So you have your distance, and then you know how much you come down and how much you will rotate across. So usually phi only goes from 0 to pi. And we can have pretty easily some conversions. Imagine this line coming out like this. We know the z value of this is just going to be, so I convert it. So if we look at this triangle right here, then the height is going to be, the z is rho cosine phi. That's rho cosine phi. And this length right here, which corresponds to sort of the r value, call it r, is rho sine phi. And then if we know this length, we can use this to find the x and y components based on this r value right here. We can find the action y, again, there's going to be r. X is going to be r cosine theta, and r is rho sine phi, so it's going to be rho sine phi cosine theta. And similarly, r sine theta is rho sine phi sine theta. That's a conversion here. And you can sort of imagine some other shapes that are easy to graph in this coordinate system. Like rho equals constant, rho equals 1, will just give you a sphere of radius 1. Fixing phi as a constant, say if equals pi over 2, will give you a cone. Because this will be at pi over 2 and we rotate all the way around and at all radius lengths. Then theta equals constant will give you just the plane coming out. So a vertical plane. And so there are various other things that can be graphed with this coordinate system, and is also useful for integrating curved linear surfaces and regions. But what is dV in this system? Well, it's less intuitive than in cylindrical, so we're going to have to try to visualize this again. Okay, let's see. You imagine a tiny, sort of a slice of okay, so say this is a slice of a sphere, sort of, and let's call this delta V. For this slice, we slice our region up into small things that look like this, but we can see that it looks kind of like, let's start labeling things a little bit. This is the rho value right here. This is the slight change in it all, this slight increase, delta rho. Here's phi, and this thing right here, drop it down. This is your theta. And this, excuse me, a small arc right here is delta theta, because it's going this way, whereas this is delta phi. So now we can sort of imagine this as approximating a sort of rectangular prism whose area, as we know, is the area of the base times the height. The height is delta rho. So it's approximately this surface area S times delta rho. So now what is the surface area? Well, it looks sort of like a rectangle itself. And we can approximate this one as well. S can be approximated by this length and that length. And so this arc length right here is not exactly the same as this one right here, but as delta phi gets smaller and smaller, they will get closer and closer. Similarly, this arc length will get fatter and fatter and approximately a straight line as these get smaller and smaller. So this one right here, this is part of a great circle. The radius is rho, as we said. So this arc length right here is approximately, here we go, this shape. So this arc length, this is delta phi, this is rho, this arc length is rho delta phi. This is r, the radius times the angle, to give you the arc length. And this length right here is also going to be the radius times the angle. And we know the angle is delta theta. But what is the radius? The radius is r. So at this height up here, this forms part of a circle, but it's not, the radius is not at all. It's in fact this length right here, which is r, which we know is rho sine phi. This is this part right here. So the arc length here is rho sine phi delta theta, and so the S, the surface area of this, we approximate it like the area of a rectangle, is going to be these two multiplied together. So rho times rho is rho squared sine phi delta phi delta theta. And of course, this times the delta rho to get it to be a volume gives you your final delta V approximated by rho squared sine phi delta rho delta phi delta theta. And as of course each of these gets smaller and smaller and smaller, closer and closer to zero in the limit, we get dV equals, this becomes an exact quality, rho squared sine phi d rho d phi d theta. This is also an important formula to remember. So that's what dV is. And so you can integrate triple integrals in spherical coordinates, and here's a conversion from x, y, z, and your dV becomes this. And most of the time, this will be the order of your integration, rho, phi, and then theta. Because most of the time, you'll have figures that look something like this. Something that's curved. And so you want to find out when does the rho enter, and then when does it exit. So you find these bounds, you integrate d rho, and then, so this would be a function of phi and theta. And then we would say, well, how does the theta change for each one of these points? So if I fix my theta, this slice, how does the phi change from this angle, phi 1 to phi 2? Or in general, as a function of theta, probably. And then, of course, you want to see where does this theta start, and then how far does it go? So theta 1 to theta 2. And of course, there's also going to be this part as well, rho squared sine phi, and then, yeah. So this is how you do it in general, in spherical coordinates. It's a slightly more complicated formula to know, but it's very useful for spheres and shapes like that. Cylindrical is for cylindrical and shapes that are kind of rotated around the z-axis. You would use cylindrical. And that's sort of an introduction on cylindrical and spherical coordinates for triple integration. Thanks for watching, and I'll see you in the next video.